This video is about matrix equations. For our notes, let's actually start by reviewing matrix multiplication. We've done this recently, and we want to review it with this probably strange looking example to do so. We have a 2 by 2 matrix which reads 2, -3 across the top row, and then 1, 5 across the bottom. And then we have this 2 by 1 matrix that simply has the variables x and y in it. So x on top, y on the bottom, 2 rows, 1 column. And so we want to just multiply, so that's a 2 by 1, but recall these are multipliable because these inner numbers match in their orders. And in fact, the result would end up being a 2 by 1 matrix. So let's go back through the process of matrix multiplication. Remember, you'll multiply the top row times, there's only one column here, and then we'll add the entries in the following way. We'll say 2 times x, so that's 2x, plus -3 times y, so plus -3y. Okay, and then for the second row, we'll say 1 times x, which is just x, times, plus 5 times y, like you see it. Now, okay, you may not have an idea of what we're doing at this moment, but look at what just happened. We multiplied a 2 by 2 matrix full of numbers times a 2 by 1 matrix full of only variables, and what we got is interesting. It looks like just expressions, variable expressions, right? We have 2x plus -3y. Of course, you could say that's 2x minus 3y. And then secondly, we got x plus 5y. So, okay, what are we doing? Well, that's where we're going next. But first of all, just recognize that that was simply matrix multiplication that occurred. Now, moving on, we can create a matrix equation by setting something like the above equal to a constant matrix such as. Now, if you take a look at this, we have the matrix that we started with above. That's our 2 by 2. Again, those entries are 2, -3, and then 1, 5. That's going through the rows of that matrix, matching the one above, times our variable matrix, again, a 2 by 1 variable matrix with x over y. And then we have it now equal to a constant matrix that is also a 2 by 1, 2 rows, 1 column. Those entries are 6 above a 4. Okay, now, if you kind of connect what we were just doing with the matrix multiplication at that last exercise above, then you get something rather interesting. Let's do the exact same thing, but this time, notice that when you multiply those matrices together, which we've already done, like the first entry turned out to be 2x minus 3y from above, and then the second one turned out to be x plus 5y. But now, if we take those expressions and set them equal to their corresponding values, so notice if we were to put that result in the previous part really in a matrix, it's like you have a 2 by 1 result matrix, right? Where the 2x minus 3y is the top entry, and then the x plus 5y is the second one, bottom entry. If we set those two results equal to the entries in the constant matrix, we'd have 2x minus 3y equals 6, and then we'd have x plus 5y equals 4, using those entries from that constant matrix. Interesting, what just happened? We have what looks very familiar as a system. So I'm purposely going backwards in this because I think it helps kind of show where and how all these pieces connect. Now, the reason we might care about a matrix equation is because if you go back and recall the notation I had kind of floating above this previous step here, right, there was a capital A for matrix A. Notice that I called the variable matrix just a big capital X, and then the constant matrix I called capital B. All right, so just keep in mind those variables. If we use the matrix equation we just got, of course it turned out as AX equals B. Well, it turns out we can solve a matrix equation just like we could solve a regular real number algebraic equation. But there's one slight difference. In algebra, if I wanted to solve for x in this equation, I would simply divide by a on both sides, right? Cancel the a's and go from there. Well, okay, fine. It turns out, though, that you can't actually divide by a matrix. Yet, I still want to get rid of matrix A so that matrix X is alone, which would mean I solve for X and I'm done. Okay, so instead of dividing by A, what we're allowed to do is multiply by an inverse. So I'm going to sneak in an A inverse on the left side of A. But here's the deal. Remember, with algebra, whatever you do to one side of an equation, you have to do to the other. Well, it's even pickier with matrices. If I multiplied by A inverse on the left side of the left side, then I have to multiply by A inverse on the left side of the right side. So on the right side now I have to put A inverse and I have to squeeze it in just to the left of B. The order matters here. Now, once we do this, of course, A inverse times A is the identity matrix as we defined way earlier. Those cancel out, giving us only matrix X on the left side. And then on the right side, we have this A inverse B, but that's just a product of two matrices, the inverse of matrix A times matrix B. Well, let's recall that matrix X was our variable matrix containing only the X and the Y. And then if I know matrix A, then I can find matrix A inverse and multiply it by B as well. In fact, let's do this right now. Let's go back up and recall what matrix A was. We want to find out what A inverse B is. And we know we can do that even just on a calculator if we know matrix A and B. And we know them. They're right here. So let's go ahead and take out our graphing calculator again. Turn it on. Okay, now I went ahead and typed in the matrices we have in this problem in as A and B in the calculator, exactly as we have them as A and B in this problem. So we want to now compute A inverse B. Okay, now there's a bit of a shortcut to this as far as the inverse goes. You may recall we've already calculated inverses and we did it using the row operations with the identity matrix. And we used a calculator for it, and that's fine, but there's even a faster way, and when we do these matrix equations, it just makes a lot of sense to do this. So I'm going to multiply matrix A inverse times B, and here's how we can do that. We'll hit second matrix. We're going to find a matrix A, but we're going to use this inverse key that has an X with a -1. If we hit that, it puts a little -1 in on the top corner of the matrix A. Okay, that actually means A inverse, just like you see it when we write it by hand. That's what we want, but we want to multiply that by matrix B, so we'll do times, and then we'll do make. By the way, in the TI-84 Plus, you don't even really need to put the times symbol. If you just smash two matrices together, it'll assume you want to multiply, but I'm just putting it there for clarity. Okay, so I want A inverse times matrix B, so now we'll go second matrix, and then I have, as I said, matrix B typed in, given as the B in this problem. If I hit enter for A inverse B, okay, it gives us a whole bunch of nasty digits, but we can convert that by hitting math and then the fraction button, and sure enough, there it is. Okay, so thanks to the calculator's help, this simple matrix equation was solved with just a couple button pushes, and we have our variable matrix of x, y, x over on y. It's equal to 42/13 for x and 2/13 in the y spot. In fact, that's exactly what it means. Those variables are lined up with their solutions. So we could write this as an ordered pair solution where 42/13 is the x value and then 2/13 is the y value. And of course now it's in the usual solution form of an ordered pair for a system. And so we just solved the system with a matrix equation. Let's try another example where we want to solve the system as a matrix equation, but this time we're given only the system. So we have a system of two linear equations here. The first equation reads -7x plus 4y equals 0. The second equation reads 8x minus 5y equals 100. So we're going to do from start to finish everything involved in this one. The first step would be to convert our system to a matrix equation. Okay, so we're going to start out with a matrix containing only the coefficients of all our variables in their order. Remember, the x's are lined up vertically, so are the y's. So we want a -7 and then a 4 across the first row, and then an 8 and a -5 across the second row. That's our coefficient matrix, what we were calling matrix A in the previous little example there. We're going to multiply that by the variable matrix, which our variables are x and y in that order. So we'll call that the x matrix. And then that's equal to the coefficient matrix, which for this system would be the 0 and the 100. And that would be like our matrix B. Okay, well, once we can take a system, turn it into a matrix equation like we just did, that means we can solve it in general like we just did previously, where you multiply by A inverse on both sides. So x will end up being A inverse B. And we can simply now type matrix A and B in the calculator, compute A inverse B, and get a result very easily. Okay, computing this result in a graphing calculator yielded the following result matrix for A inverse B. Remember, this is just a 2x1 constant matrix. The first entry is -400 thirds, and the bottom entry is -700 thirds, which means, again, that if you kind of line things up with how the variable matrix was set up, the first variable was x, the first entry would then match what that is. So that means our x value is -400 thirds for our solution. Of course, the second value is the y value, so -700 thirds would be the y value to the solution of this system. And that's, again, solving a system that started just as a regular old linear system of equations, and we solved it using a matrix equation.